Hi team, today we're going to be working with negative and zero exponents. So for a warm-up, I just want you to go through and try these 5 problems and just simplify them as much as you think you can and see what happens. Alright, hopefully you had a chance to go through and work these. So I'm just going to go through and give you my answers. So for number 1, 10 divided by 10, anything divided by itself is going to be 1. So if I look at number 2, x divided by x, this is also going to be equal to 1. If you want to think about this in terms of your properties of exponents, we're really lazy and we don't put the x to the first power there. It's just implied that the exponent is 1. So if we were to use our rules of exponents that we learned yesterday, we would do subtraction because we have like bases. And 1 minus 1 would give us 0, which is kind of interesting because x to the 0 is maybe not the same thing as 1. We'll have to see. For number 3, 10 cubed divided by 10 cubed. Again, if maybe you wanted to try the properties of exponents here, you could do the subtraction. So this would be 10 to the 0 power. But keep in mind, this is really, if you want to think about it in simplified form, 1,000 divided by 1,000. 10 to the third power is 1,000. Anything divided by itself is going to be 1. So that's kind of interesting here. It's telling me that these two things right here have to be equal to each other, just like what was happening up here. Let's look at number 4. Same idea, same base, so we can go ahead and subtract the exponent. So this is x to the 0, but we know anything divided by itself is going to be equal to 1. So maybe we can use that information to help us with number 5 here. So notice inside of these parentheses, that is the exact same thing. So anything divided by itself is 1. 1 to the third power, remember, is equal to 1 times 1 times 1, which is equal to 1. So again, that all 5 of these had the exact same answer of 1. So for our note sheet today, you can go ahead and print this out. And again, note the different colors on here. So we're going to just start with following the pattern. So I want you to kind of take a look. I have 2 to the third power all the way down to 2 to the negative third power. And let's just look at these, the pattern properties that we see here. So 2 to the third, remember that's going to be equal to 2 times 2 times 2. So that's 8. 2 squared is 2 times 2. That's equal to 4. 2 to the first would just be one factor of 2, so that's going to be 2. 2 to the 0, I'm going to tell you, is equal to the 1. We saw that on the warm-up problems where anything to the 0 power was actually, in fact, equal to 1. And then 2 to the negative first, this is where it starts to get interesting, is actually equal to 1/2. 2 to the negative second is equal to 1/4, and 2 to the negative third is equal to 1/8. So if you kind of notice this pattern going down here, every time I'm moving down in this table, I am dividing by 2. 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1, 1 divided by 2 is 1/2, 1/2 divided by 2 is 1/4, and 1/4 divided by 2 is 1/8. If you want to look at it like this, you could also think about 2 to the negative first power is equivalent to 1 over 2 to the first. 2 to the negative second is equivalent to 1 over 2 squared. And 2 to the negative third is equivalent to 1 over 2 to the third power. Now that's not directly obvious here, and we will spend a lot more time talking about this, but go ahead and take a moment and see if you could fill in the pattern for these powers of with base 3 and then with base 4. All right, hopefully you had a chance to do that. So let me go ahead and fill in my answers here. So 3 to the third power would be 3 times 3 times 3, so that's 27. 3 squared is 9. 3 to the first power is just the same thing as 3. Anything to the 0 power is 1. And then 3 to the negative first power, I'm going to kind of look and see what happened over here with 2 to the negative first. It looks like we put 1 over 2, so here I'm going to put 1 over 3. And then notice that's also following my pattern of dividing by 3 as I work my way down this table. 27 divided by 3 is 9, 9 divided by 3 is 3, 3 divided by 3 is 1, 1 divided by 3 is 1/3. So this is actually going to give me 1/9. And then 1/27. And same idea with my base of 4. 4 cubed is 64, and then we get 16, 4, 1, 1/4, 1/16, and 1/64. So kind of the big thing here that we should be looking at, and we can look at any one of these columns in our table, but 4 to the third and 4 to the negative third, notice they both have 64s in them, but it just changes where they go. 4 to the positive third power, the 64 was in the numerator, and 4 to the negative third power, all that did was move that 64 to the denominator. So what do we notice here? Hopefully two big observations. Anything raised to the 0 power is 1. And then the other thing, and we'll talk a lot more about this on the next page as well, negative exponents are, we're going to call them movers, because what happens when we have something raised to a negative power is it's moving its location. All right, on the back side here, I have 6 problems, and just to kind of go through and simplify them, 1, 3, and 5, you should be able to do no problem. Same base, so we can go ahead and subtract the exponent, so we'll go ahead and do that for number 1. So this would be x to the 5 minus 2 power. So this would be equal to x to the third. The other way I like to think about these is there's more exponents up top. X to the 5th has more factors of x than x squared. So these two factors take away 2 of those factors. And you might be able to see that a little bit more clearly if I take a moment here and actually just write them out. So here's x to the 5th. Here's x squared. And so if I think about this, I can see common factors in the numerator and the denominator. These factors of x would cancel each other out because I'm dividing by the exact same thing, leaving me with 3 factors of x up in the numerator. So compare that to number 2. There's now more factors of x in the denominator, so these 2 factors of x up top would take away 2 of those factors of x. Since I lost my numerator, I'm going to need to keep 1 as my placeholder up there. And so I'm left with 1 over x to the 3rd power. If you want to see it written out like I did number 1, there's x squared. There's x to the 5th. So then any like factors in the numerator and denominator, since everybody's being multiplied together, I can go ahead and reduce those out. And so then you can see that we're left with those 3 factors of x, but notice their location, they are down in the denominator. So that 1 up in the numerator acts as my placeholder, and then I'm left with 3 factors of x on bottom. Now, if you were tempted to do what we did in number 1 when we first started and to subtract these, you would have done x raised to the 2 minus 5 power, which gives me x to the negative 3rd power. So I got 2 different looking answers for the exact same problem. So that tells me that 1 over x to the 3rd and x to the negative 3rd power have to be equivalent to each other. Let's see what happens with 3 and 4. So with 3, I don't really want to write out 10 factors and 7 factors of y. That's starting to get too many factors for me to fit on my page. So 7 factors on bottom take away 7 of the factors on top. I know that because there's more factors on top. 10 is bigger than 7. So this is going to leave me with y to the 3rd power. Now, if I see it flip-flopped with the numerator and denominator switching spots, there's now more factors of y in the denominator, so those 7 factors are going to take away 7 of those factors, and I'm going to be left with 1 over y to the 3rd power, which, note, is equivalent to y to the negative 3rd. Had I done 7 minus 10, I would have gotten y to the negative 3rd power. Just to note, this is going to be how we want to write our answers. Y to the negative 3rd power is correct, but negative exponents are not written in good mathematical notation, so we want to focus on having positive exponents. So let's look at 5. A to the 11th divided by a to the 10th. There's more factors on top because 10 is bigger than 11, so 10 of these factors will cancel out, leaving me just with a to the 1st power. And note, I can certainly be lazy and just write that as a. Then for number 6, There's now more factors in the denominator, so those 10 factors will take away 10 of those factors. So I'm left with 1 over a to the first, which I could rewrite as just 1 over a. So what do we notice here? Well, hopefully you're starting to see this kind of negative exponent pattern. So I'm just going to use generic letters here. So b to the negative nth power is equivalent to 1 over b to the n. Okay, if this was up here in the numerator, this now moved down to the denominator. And we'll just write this again. Negative exponents are movers. Notice it didn't make any of my values negative. It's just moving the location, numerator or denominator, within my fraction. So let's look at kind of a bunch of examples. So all of these have to deal with either a squared or b cubed, and these are going to vary depending on which one of the exponents is negative and what the initial location to start with for each of the bases. So we only have issues with negative exponents. So in this first one, I'm going to identify which one's the negative exponent. So that happens to be the denominator. So since negative exponents are movers, to make that a positive exponent, I'm going to move its location. So if that's in the bottom of the fraction, that's going to move to the top of the fraction. A squared was not negative, so it is not going to move. That's going to stay exactly where it was originally. So this would be my final answer. I can't do any more simplifying from here because I don't have the same base. Now look at b. It's now my numerator that has the negative exponent. So that needs to move. That's going to move down to the denominator. Notice b cubed has a positive exponent, so don't touch it. Now that I lost my numerator, we're going to go ahead and put a 1 there as my placeholder. And then for c, notice both of these have a negative exponent. That means both of them are going to move. B to the negative third becomes b to the positive third power up in the numerator, and a to the negative second becomes a to the positive second down in the denominator. Let's try a few more. So these ones now have, instead of the division like we saw in the last one, these are now being multiplied together. So this tells me that b to the negative third power up here, that's the one I need to move. So a squared stays where it is, so it's in the numerator. And if you want to kind of visualize this, you can always put something on top of 1, and you can kind of see it now as a numerator and the denominator. That tells me b to the negative third is going to have to get moved down to the denominator, and doing the moving is what eliminates the negative exponent. If the a was the one that had the negative exponent, that means b to the third doesn't move because it has a positive exponent, and a squared moves. And then if both of these are raised to the negative power, that means both of them are going to move. Now, what about something like this? These ones sometimes throw people for a loop. If I'm looking at g, I'm going to see what's raised to a negative power. The b is raised to the negative power. Notice the a is not. This is still a to the first power. We're just lazy and we don't put that 1 there. And then a to the negative fifth is also being raised to the negative power. So both of those are going to move to where they are not. That means b to the fourth is going to go down to the denominator, and that means a to the negative fifth is going to go up to the numerator. And that's going to be a positive, positive a to the fifth up in the numerator. Now this one has an added element here because notice I now have 2 factors of a, and so I can use my properties of exponents to go ahead and simplify them. So I might want to put that little 1 in there again just to remind me that's a to the first power. So when I have the same base and those bases are being multiplied together, that's when I go ahead and add the exponents together. If you ever forget and you start feeling confused as to do you add the exponents or do you multiply the exponents, you could go ahead and write out what a times a to the fifth looks like. And then notice we have 1, 2, 3, 4, 5, 6 factors of a. So that helps remind me that I should be adding my exponents for this problem. All right, for h here, notice I have all of the same insides. So if we want, we could go ahead and simplify the insides first. I guess let's go ahead and do that. We'll look at this one 2 different ways. So this will be a to the 6th over b to the 4th. But note, we still have this exterior exponent of 0. And keep in mind, what happens when we raise something to the 0 power? Well, it turns into 1. Anything to the 0 power is 1. So this problem right here, say I hadn't done all the preliminary work that we did in part G, I would have noticed that I don't care what's on the inside, but I do care that that whole thing is being raised to the 0 power, and I could have just automatically jumped to writing my answer as 1. All right, let's take a look at this one. Lots of stuff going on here. I see every single base as x, so that's, I don't know, I guess exciting. And then I see a whole bunch of different kind of things happening with the exponents. X squared is positive, so for right now I'm going to leave it just where it is. X to the -7th. I like to deal with my negative exponents first. It's not the only way, but that's just kind of my personal strategy. So I'm going to move that down to the denominator, so that way I have to the +7th power. And then notice in the denominator here, x squared raised to the 3rd power. Power raised to a power is when we multiply. So 2 times 3 is 6. Again, on that one, if you start to get confused, that can be x to the 6th or x to the 5th. Think about what it means to raise something to the 3rd power. It means to multiply it by itself 3 times. And then you could even break that down further. X squared times itself 3 times. So now there's 6 factors of x. All right, so let's look and see what we have here. We moved everybody, we did a bunch of simplifying, but I still have the same base, so I know I can write these a little bit better. So I'm going to clean up my denominator, x to the 7th times x to the 6th. Notice same base, and we're multiplying them together, so we're going to add our exponents. And then lastly, I still have the same base here, but now I'm doing division. So I have 2 factors of x on top and 13 factors of x in the denominator. So these 2 factors of x will take away 2 of those factors of x. So this is going to leave me with 1 over x to the 11th power. I want to add in just a couple more here just to kind of show you some things that can happen with your negative exponent. So how about 7 times y to the -1st power? So something like this. Again, identify what's being raised to the negative exponent. It is only the y. It is not part of the 7. So that means that 7 is going to stay where it's at. And then this would be 7 over y to the 1st power, which that would just clean up to 7 over y. Notice that difference if I had parentheses here. If this was the quantity of 7y raised to the 1st power, that means everybody inside of these parentheses is getting raised to that negative exponent. So that means that entire thing would move down to the denominator and be raised to the 1st power. Raising something to the 1st power doesn't change anything, so that would stay 1 over 7y. What if that were 7y raised to the -2nd power? Well, that's going to look like the same thing. It's going to be that quantity squared. And then notice, raising something to the 2nd power, the 7 gets squared and the y gets squared. So this would be 1 over 49 y to the 2nd power. You also could have thought about this step right here being squared. That is 7y times 7y. So that might help you see, hey, there's the 49, because big numbers still get treated like big numbers. 7 times 7 is 49. And then y times y gives me a y squared. What if that looked like 7y to the 0 power? Well, something like this, remember, anything to the 0 power is 1. So since it's only the y that's being raised to the 0 power, this is really like 7 times 1, which is secretly 7. If this was 7y, the quantity of 7y raised to the 0 power, now everything inside of here is getting raised to the 0 power. It's like 7 to the 0 power times y to the 0 power. This is 1 times 1, which is just 1. Now, that was a lot of steps to get there, so I would just say, hey, if that whole quantity is getting raised to the 0 power, you know that that quantity is going to be just 0. Now, let's take a look at just a couple more, and then that will be it for today. What if it was -7 times y to the 0 power? So this would be -7 times 1. Because notice y to the 0 is equal to 1, so negative 7 times 1 would give me negative 7. And then lastly, what if it was negative 7y, that entire quantity raised to the 0 power? So again, anything inside of here, if that whole thing is getting raised to the 0 power, that would just give me 1. Homework for tonight is going to be 13.3 in Connect Math, and it's going to be negative and 0 exponents. There's a lot of kind of just playing. I really encourage you guys to write these out and to really look and see what happens. There's a lot of simplifying that's going to happen, and there's a lot of opportunity for you guys to practice all of the different exponent properties. Good luck, and please let me know